Okay, so welcome to my talk. I'm going to be explaining industrial control systems to a full overtook. So this won't be very low level. It'll be high level. It'll be explaining what I've been learning over the last few years, what I've been interested in for the past 6 years, and so yeah, I'm a software engineering teacher. I'm a second-year PhD candidate, so this is the area that I'm researching in. And that's in industrial cybersecurity. So lately I've been trying to spend more time outside than inside. So I love coding, it's what I do for my job, but you'll find me with a book more than you'll find me coding these days in my spare time. So firstly, a disclaimer. I could talk for Wales, it's probably good I have 45 minutes. I'm here for fun. It's not part of my studies or my job, but I will be talking about some of the equipment that we do have at work, and expressing some personal opinions, so it doesn't reflect where I work. And I finished teaching at 4 p.m. yesterday, so I'm pretty tired. I got to London quite late. So I'm not funny, but I joke when I'm anxious. So there will be jokes in here, and they will be awful. So I'm sorry about that. So I'm still learning myself. So if I'm incorrect, tell me later. Maybe not in front of everyone if it's really embarrassing, but you can call me out if you want to, but just come find me later, talk to me, because I'm still learning and I want to learn from you, and I'm hoping that you're all going to learn from me too. So we have a problem. We have a problem. And our problem is it's possible to hack things. We rely on things. So that is the premise of this whole talk. So, we're reliant on technology. Going back about maybe 100 years, we wouldn't be reliant on technology for a fraction of the things I'm about to talk about. Things would have been done manually, they wouldn't have been automated. And there wouldn't have been so many problems happening. There would have been a lot of human error, but less technical error. So this is what this talk's going to be about. So from the watch on your wrist, to the thermostat in your home, to the machine that squeezes your orange juice, and the app you use to buy your train ticket, which I imagine almost all of you did if you used the train to get here, and to the card machine that takes your payments. And I know even in the last year we've had issues where card payments, like MasterCard has gone down or Visa has gone down. It's good that a lot of people have at least one or the other so they're able to pay for something. So there's more. So I want you to imagine, and no, not that, but that's what came to my mind when I made this, because I was going to say, I want you to imagine a scenario. But then I'm one of the people that if I'm told, I want you to think about a red apple, I can't visualize a red apple unless I'm literally just about to fall to sleep. So I'm one of those people, and you probably didn't need to know that, but so I want you to imagine, firstly, you have a thermostat in your home. It controls the temperature. If someone hacked into that, how would you feel? They could make it probably quite hot, but I imagine there's fail-safes there. It won't be able to get too hot. It'll waste a lot of money and it might be annoying, or maybe it'll make it really cold, and that would be really annoying too. But you wouldn't die from it, it would just be annoying. So let's have a think, what about medical devices? For those of you that were here for the opening talk, we were asked not to hack into BLE devices, so insulin pumps, that kind of thing, that people here today might be walking around wearing. But that's on a bigger scale. We use technical devices in hospitals that can be hacked into, and these might be connected to the internet. What do you think about that? How about traffic lights and train signalling systems? What happens if you hack into them? What about a nuclear reactor? Same premise as a thermostat. You know? Gets too hot, it cools down. Gets too cold, it increases. Very simply put. What happens if that goes wrong? So, when I proposed this talk, there were 13 pillars upholding society. have chemicals, civil nuclear, communications, defence, emergency services, energy, finance, food, government, health, space, transport, water, but there's a 14th now. So one thing about all of these is that could we go without them? Previously, they weren't reliant on technology. Or not the technology we know these days, the interconnected electronic technology. But now they are all reliant on each other. So we now have a new pillar, data centres. So the 14th sector has been added as a critical national infrastructure in the UK. And these are seen as critical to society's functioning. And I have the definition in the next slide. This was announced by the UK government as of the 12th of September this year. This makes a lot of sense. How many of these rely on data centres now? Everything's in the cloud. Are people running their own servers in their own business locations? No, a lot of them are working from home. A lot of them don't have business locations. And yes, you have the big data centres that you can rent out, and then companies do have their own data centres, and they would both be part of this. But one has a lot more, one's probably, it's interesting actually. So I would say you have more control over your own data centre. Then if something goes wrong, like a flood, you're not really covered. But you have a lot more control over your data. But then if you save it to a large data centre, a large data company, and I can imagine you're all thinking of company names right now, they might have like 3-4 backups of your data across the world, just in case one location goes down, so you always have access. So it's about weighing it up. So, critical national infrastructure, according to the NCSC, are national assets that are essential for the functioning of society, such as those associated with the energy supply, water supply, transportation, health, and communication. So, they're classed as critical for maintaining life as we know it. So, the first thing I'm going to talk to you about is cybersecurity demonstrator. What is that? So, they are shiny things used to convince C-suite execs to spend money. And they like flashy things, the C-suites do. The lights go out when bad things happen. So just like I was asking you to imagine things, think of the apple. Those of you who can imagine the apple, you would have maybe really been able to imagine what could have gone wrong. And those of you who can't, maybe it was a bit more difficult. So these are visual, physical things in front of people that show them exactly what can go wrong. So it's chaotic good. As money spent on cyber is money well spent, and you're all here today, so I assume all of you are on the same page as me there. So they're not always useful for actual cybersecurity research. Some might just have some Python code or an Arduino running these simulations to show what would happen, but some might have actual PLCs under the hood controlling it. And then you can actually run actual cyber attacks on them, and then they will demonstrate what can go wrong. So I'm going to show an example here, and I've got 2 people in the room here who will recognise this. So this is one from work, and this photo was literally taken yesterday. And to me, it's pretty cool, and I wish I could have put a video in here, but I wasn't sure how it would show up. But it runs through phases of what happens as different areas of national infrastructure go down. So it allows C-suite execs to come in, see what could happen, and then figure out what they need to do to make sure that doesn't happen to them. So, industrial control systems, what you're all here for, right? So the example I've always gone for, so this is actually, I think, the third talk I've given to do with operational technology or SCADA systems or industrial control systems. I always go for the thermostat example. It's my favourite. And as this is explaining ICS to a fool of a toque, and for those who don't understand the reference, it is a Lord of the Rings reference. Fool of a toque is it's a halfling reference. So my mind's gone blank. Peregrine toque. So thermostat set to value. So we're going very simple. You set the thermostat temperature to a value. If temperature is equal or more than said value, the heater is off. If temperature is less than said value, heater is on. Sometimes people make out that this is a really complex topic. It's not. It's a control loop. So the sensors pick up signals. In these systems, you have sensors, and they pick up signals. In this case, that would be temperature. The actuators, such as a motor, would then make a change. And it is that simple. So, a lot of buzzwords here. You have operational technology, industrial control systems, SCADA systems. And I think one thing about this is that it's happened over time because there are generations, and for example, IIoT, Industrial Internet of Things, that didn't exist when SCADA systems existed. So all these new buzzwords are popping up all over the place because people are coming up with new terms. So OT, operational technology, ICS, industrial control systems, SCADA systems, supervisory control and data acquisition systems, DCS, distributed control systems, and then on the side, industrial Internet of Things. So there are 4 generations of industrial systems. You have monolithic, distributed, networked, and industrial IoT. So the first generation, monolithic, these were built around the 1960s and 1970s, and I am generalising here. There might be some that were built after then, but I'm generalising. So these are called monolithic because they were large mainframes. And they're still in use today. They should be air-gapped and controlled locally. This means that rather than connecting to it externally, you would have to be in the room with it connected directly to it to control it. Second generation, distributed. You can then have smaller systems with more powerful mainframes connected through a local area network. You can then control it, maybe in the other room, maybe in another building, but it isn't as large as the internet. So this allowed for an increase in interoperability between systems. So the third generation, networked. These were built in the 1990s, and they increased network connectivity and interoperability even more. So the network protocols that were being defined in 1990 allowed for the increased network connectivity and interoperability. So before then, the connections between these systems wasn't defined by these protocols. So the fourth generation, industrial IoT, so this is much more recent, built 2000s. These systems are linked via an API, or they can be, to human-machine interfaces, such as web applications. But these 4 generations, they don't all stand alone. They're all interconnected because critical national infrastructure uses a plethora of these 4 that have all been bodged together. And if you could imagine that the first generation is secure by air gap, and we need to connect that to industrial IoT devices, that means a network connection needs to be created, introduces security risks into the first. So I'm going to go through something called the Purdue model. So in the control loop, we talked about sensors and actuators. So these would be field devices. These are level 0. So I see this as quite similar kind of thing as the OSI model. It allows to differentiate between the different components within industrial networks. So level 0 would be field devices, such as sensors and actuators. One would be local controllers. So these would be programmable logic controllers and remote telemetry units, among others, because I will have a slide for each of these. Level 2, that's local supervisory. So human-machine interfaces and historians. Same for 3, but there is a difference, which I will go through. So 3 is site-wide supervisory. 4, business networks, workstations and local servers. And 5 is enterprise networks, so enterprise Active Directory and enterprise SOC. So this was created by Theodore J. Williams, and the data I'm going to be using in the next 6 slides comes from the Introduction to ICS Security Part 2. So I'm going to be going through that, but it comes from their course. So level 0, field devices. So these are, like I said, sensors and actuators for the cell, line, process, or distributed control system solution. It's often combined with level 1. So these can include basic sensors and actuators, smart sensors and actuators, and speaking field bus protocols, that should be 2 separate bullet points there. Intelligent electronic devices, industrial Internet of Things devices. We talked about IoT earlier, so they go in at level 0. And communication gateways. So level 1, often combined with level 0. Devices and systems to provide automated control of process, cell, line, or DCS solution. Modern ICS solutions often combine level 1 and 0. Like I said, this has come from SANS because it's just, everyone describes it slightly different, and this is the version that I like. So PLCs, control processors, programmable relays, RTUs, and process-specific microcontrollers. When you break it down, it's really quite simple. Local supervisory. Monitoring and supervisory control for single process, cell, line, or distributed control system solution. Isolate processes from one another, grouping by function, type, or risk. So, again, HMIs. Alarm servers, process analytic systems, historians, control room, if scoped for a single process and not the whole site. So then we have the site-wide supervisory, which is similar to 2, but site-wide, again, very simple. Monitoring, supervisory, and operational support for site or region. So management servers, HMIs, alarm servers, analytic systems, historians. Then we have the DMZ that splits the OT from the IT. Now we're on to what you would usually expect within businesses. So we've got business workstations, obviously, local file and print servers, local phone systems, enterprise Active Directory replicas, and I don't think we have another one there. So that split, the DMZ, you would have firewalls between your OT and your IT. And that's really important. But not a lot of organisations do that. A lot of organisations would have people working on workstations within the OT network. And that split is one of the things that can be done and enforced to decrease risks. So enterprise networks, corporate level services supporting individual business units and end users. These systems are usually located corporate data centers. So, servers providing Enterprise Active Directory, internal email, customer relationship management systems, human resource systems, document management systems, backup solutions, Enterprise Security Operations Center, and that's it. So the reason I've used that from the course as it is that data is just, I couldn't put it better myself. And sometimes when you're trying to relay something, going with something that you know works is good. So, moving on, how do you control these controllers? Well, we use something called ladder logic. So it's a language used for programming PLCs. And it took me a while to get my head around the fact that it wasn't this very complex language that I was terrified to learn, because it's actually created for engineers working on these systems to be able to visually control the circuit diagram. So I was terrified to give ladder logic a go, and there was no reason to be. So it's one of the main languages used for programming PLCs, like I said. So it looks like a circuit diagram with power flowing across, running one line at a time. So I think last summer I had a student write ladder logic for their dissertation, and it was just really fun to get involved with it. So it's one of the IEC 611313 standard languages, and I'm glad I read that right, because dyslexia. So industrial specific network protocols. This could be a talk completely in itself. So I won't be talking through each of these, but I will be showing you some test beds that are used for attacks on Modbus and CAN bus. So the list there: Modbus, CAN bus, Profibus, Profinet, and I got someone in work looking at Profibus and Profinet, so hopefully he can come to one of the B-sides in the future and do some talks on that. EtherCAT, CIP, CNX, had a dissertation student look at CNX last year, so if anyone's interested in that, I can send you across his report. AMQP and BACnet. So that is definitely a talk for another time. They are a massive area to talk about. And I do want to focus on the equipment and keeping it simple. So let's look at some cyber physical system test beds. So these are the ones that I'm lucky enough to be involved with or use, play with, you know. It's really fun. So I did the Hactronics course. They came into the university. So this is a course using the Bristol University box shown in the image. So we wrote scripts to reverse the direction of a factory I/O conveyor belt. And we exploited a vulnerability in VNC. And it was run by Professor Awais and Rashid and Dr. Joe Gardner. And it was honestly a really, really great course. So the second one was a SANS ICS course. This was provided for postgraduate students, which I am at my university. So they came in and did a full day course. We used PLC and OpenPLC for this. And I would say it was a very different experience to the Hactronics course. I think I learned better myself through the kind of lecturing that Joe does, definitely. This was very Americanized, very sales pitchy, but there was a lot of really good information there, and I learned a lot from it. So that's just personal opinion on it, but it is a really good course. So they're the two that I've been involved with through courses, but then back at work we have an oil and gas rig. It's in the cyber lab, and it was built by David Savell for Abu Bakr Mohammed's PhD. So using this, Abu managed to detect a field flooding attack, which is a man-in-the-middle attack, which he was able to do a DDoS on the PLC, and he actually recreated this on 3 other testbeds, and that became his PhD. So, and if anyone is interested or wants to talk more about this equipment later, we've got 2 security engineers from work in the room right now, so you can have a chat with them. We also have a smart city with a Hornby Railway, so anyone that knows me would know why I'm quite excited about being able to play with this. I can play with a model train at work, so that's really cool. So it uses a Schneider Electric PLC that controls the train. It uses a Siemens S7 PLC that controls the smart city. And it's a demonstrator, but it's also a testbed. And it was one of the testbeds that Abu, who I mentioned in the previous slide, managed to detect his field flooding attack on. And the third one was, I think he had access to a manufacturing testbed up in Tallis, up in the valleys. So those were 2 of the 3 that he managed to detect them on. So we also have a car simulator. So if you've been to quite a few B-sides, you would probably recognise this because it's a replica of one that's come to multiple B-sides. So it was created by Dave Rogers, a copper horse, for the university, and it simulates attacks while driving. So it can be used for research, but it's a really good educational piece, especially when we get students in from schools, because we can show them what it's like to, if you're driving, you can press buttons, and it will show what it would be like to hack into a car and what it would feel like to have your accelerator, clutch, and your brakes cut all at the same time, all separate. But like I said, if you've been to B-sides in the past, you've probably been able to have a go on one of these. So it uses OpenCAN, which is an open source version of CAN bus. And it is both a demonstrator and a testbed. So it can show people what it's like if you hack into this, and you can actually feel it. It's a physical experience, but also because it uses the open source version of CAN bus, it can be used for security research as well. So digital twins and simulations. So what's the difference between these? So digital twins can have a bidirectional connection or one way. There are different opinions on this. So simulations are then standalone and aren't connected to the cyber-physical system. However, there is quite a lot of research out there where digital twin has been used as a term for standalone simulations. But it is the NCSC's definition that for a simulation to be a digital twin, it has to have a one-way or two-way connection to the system that it's mimicking. So what this would mean is that you could have your industrial control system and then have a connection to it, and then have a simulation that mirrors everything happening. So something changes over here, it changes over here. There's an update over here, then it updates over here. So this means that if anything needs to be patched on your system, you can run it on the mirror first to see how it goes. The one-way connection is more secure than the two-way connection for obvious reasons. But there are benefits to the two-way connection because it means that they are mirroring each other. Okay, so here's an example of one. So this was a student project. They were working part-time with Cyber Innovation Hub. It's part of Cardiff Uni. And Ben Bevan created a smart house which simulated utility usage. And then for his dissertation, he then did a waterway simulation showing what would happen if you contaminated the water. And he had quite a punny acronym. He named it SHIT. Simulation of hydrological impact treatment. I can't remember what the T is, but it took him a while to find a perfect acronym, and I think that actually ended up on his dissertation. So good on him. Another one, this is another student project. I forgot to put his name on, but his name's Yola Jones. And he used Factory.io to create a virtual, he designed a virtual factory simulation connected into Factory.io. This is the student that was using ladder logic. So it shows cascading effects visually, and I should have said this earlier when I was talking about the demonstrator. But demonstrators show what would happen if something happens to a system that affects another system, that affects another system, which we'll come back into later when I talk about how the sectors affect each other. Then you have cyber ranges. So these simulate networks in a virtual topology. So this is something else I couldn't really get my head around when I first started, because it's, as you can see on this massive server, and I thought that this was some impressive thing. I thought this thing was the cyber range and it could only come from one company. But no, a cyber range is just a virtual sandbox for cyber attack research. You could create yourself on some old hardware, put some hypervisor software on it, and so it's a project at the moment that I'm working on, is actually creating my own one from scratch to teach myself how to do this. But you can also connect the cyber range into physical devices too. So, say one of the testbeds that has a PLC on it, you can connect it into the cyber range and then use VMs to attack it. It might sound very simple, but this is something that when you're researching a whole new area, all the little things really do add up. So industrial network vulnerabilities. So one thing I'll say is that generic network protocols are used, and generic network protocols aren't secure. So all generic network protocol vulnerabilities apply to operational technology or industrial control systems or SCADA systems, whichever, that they are all different, but whichever term you want to use. So PLCs are vulnerable to DDoS, such as the field-flooded man-in-the-middle attack that the novel attack that Abu discovered. And industrial protocols lack encrypted data streams. So that's the big one here. You need to secure them from the outside because the connections inside, they lack encrypted data streams. Another one is, and it was mentioned earlier, industrial control systems use VNC, which uses unencrypted data streams. So if you have a human-machine interface that uses VNC to connect virtually to something, that's unencrypted, and you could tap that and see what's on the screen. So, the interconnectivity of the now 14 sectors. They all rely on one another. Nuclear relies on water. You cannot put a nuclear power plant somewhere unless there is water for cooling. Water relies on transport. How does it get around? You've got the systems, but then you've got bottled water. You've got the equipment that runs the water plant. Everything interconnects with each other. So it's cascading effects. It's like dominos. Finance relies on data centers, so bringing the 14th sector in. Emergency services rely on communication. Would the emergency services work without communication? So this isn't the be-all and end-all, this is just, basically, it's a very active area of research. So we're still trying to protect it. But back to the first thing anyone ever says in this area is don't breach the air gap. And I know we're having to because the four generations are merging with each other. But don't breach the air gap unless absolutely necessary. And if you do, make sure you know what you're doing. separation of IT and operational technology, OT, where possible. And then restrict access to critical systems to those trained. So for those who've been to, probably isn't many, but a couple, those who've been to my SCADA talk in the past, I did my undergrad dissertation on a information security policy for SCADA systems. And I talked to security engineers, this was back in 2016, about their systems. And they hadn't been trained in security. They weren't aware of what would have happened if someone hacked into it. One of them had worked for the Walls factory, and we had a bit of a laugh because we were joking about what would happen. You know, all the ice cream would melt everywhere if someone hacked into it and turned all the freezers off. So that's a funny one, but then you hack into, like I keep saying, a nuclear reactor, you have a different story. So train them, and you need to be able to trust them. So that's something I haven't put on here. You've got to treat your employees well, otherwise disgruntled employees aren't great. So train personnel and enforce security policy, and obviously I have to bring Stuxnet into it. Deactivate the USB ports. So diolch yn fawr iawn, thank you very much. And I have put my logo, Cardiff U logo, and the Cyber Innovation Hub logo on there. So thank you. Any questions? Yeah.
How much to blame are vendors for security problems being introduced into ICS?
Yeah,
world?
So I remember the reason I decided to look into this for my dissertation years ago was because I read the Chatham House report in my second year, and there was just the section about how there are pieces of hardware with the same serial number with added interconnectivity, and they're keeping the serial number the same, and they're not making it explicit that they now have network connectivity. So in that case, they are to blame for for making it so obvious what default admin passwords are. They are to blame. But also, I think I'm speaking from 10 years ago there. These days, that's not something I've looked into, so I'm not sure whether that's getting better. But I think there are a lot more regulations in place at the moment.
Which is great for new things.
Yeah.
But of course, nuclear reactors might have stuff nailed to the wall that was 40 years old.
Yeah, it's an area of research that everyone's trying to figure out, I guess, at the moment. Sorry, yeah?
I was just going to ask another question with like your railway networks and interlocks, like physical hardware interlocks and things like that.
Mm-hmm.
Are you seeing people moving those hardware interlocks into software?
That is actually happening at the moment. The European digitalisation, the European system of digital citizen is coming to the UK currently. So there are safety benefits, and there's also capacity benefits, which means that more trains can run at once, but it also means that it's being controlled digitally. So that is happening right now.
I'm wondering, because, without that physical interlock, I'm there just going, like, if you're looking at physical cabling now, which is what feeds into your signalling system, does that start causing issues where somebody goes through and wires something up on?
Say that again?
Well, because what you've got is ultimately you're going to have sensors on points and everything like that to start knowing where trains are and everything like that. So I'm thinking along the lines of is that if somebody wires up a signal incorrectly, could you end up in a situation where you're feeding the wrong information to the signalling system?
if it's wired up incorrectly, then you get the wrong signal, the wrong sensor signal. Yeah.
Hi there. What I'm wondering is both for academic researchers and practitioner researchers from broader InfoSec areas that want to break into this niche, what would be sort of the learning route you would recommend?
So you asking about getting into academia?
No, what I'm asking is to enter into this particular niche, right?
Okay.
Like, what would be, I do academic research in information security area, broader research, but like specifically this area, what would be what would you learn first? Should we follow the same route that you have in learning, or what would be the things you would learn first before jumping into either academic research in this or exploit development in this, etc.?
So I think I'm interested in this because I play around with things and I learn by playing around with things, but also I've read, I think, 3 textbooks back to back on the topic, one being industrial cybersecurity. I can't remember exactly who it's by. But books are amazing on this area. But reading good papers where they're not gatekeeping the secrets, they're actually teaching you through the paper. And I think if you're already in academia, you'll be able to recognise that kind of paper straight away.
Hello. This is the last question, so I'm very happy that I'm able to ask it. It's more of a similar question of the previous gentleman was asking, but in terms of practical opportunities, training, or playing around with labs, or cheaper alternatives to getting test beds or demonstrators, what opportunities are there for defensive security folk to learn about and potentially break into this industry, or to find opportunities? I know you're a software engineering teacher, but I'd love to know what your opinion is.
Okay. So, you saying that you want to use test beds?
Any practical application or environment or course, what would you recommend for someone who wants to get into the industry? They can move into a defensive security role in ICS.
So, my route is definitely books, playing with things, reading around the area, reading papers. There are some really good courses out there. We're also running courses on this where I work as well for people wanting to get into the industry. And if you want to talk to me after, I can tell you about that, but I don't want to, I'd say both of you raised a really good point in that I really struggled upskilling myself in this area because I feel like it's quite a gatekept area or gate-kept area. Everyone within the area acts like it's really complex and really impressive to be within it. Once you start to break it down and learn it, you realise that you just need to put time into it and be patient with it. But, yeah.
Sorry, can I just
Sorry, I should have said that, yeah.
But I think that's
Yeah.
Thank you.
No, I use OpenPLC, I shouldn't have. Thank you. Yeah, thanks. All good?